Hi, my name is Ho Chang Lee, and today I want to share with you a paper titled Active 3D Modeling via Online Multi-View Stereo. This presentation will contain the following material. First, a brief overview and objective of this paper. Then, I will introduce some background knowledge, the methods employed in this paper, and the experimental results will also be discussed. And finally, I will wrap up the presentation by pointing out some of the strengths and weaknesses of this study. The paper is titled Active 3D Modeling via Online Multi-View Stereo. It was presented at ICRA this year. This paper proposes an approach that can create accurate 3D models in real time during a single exploration. Compared to the traditional methods that often require multiple scans of the environment and reconstruct the 3D models offline, the proposed method is time efficient and it can achieve more accurate reconstruction. The ultimate goal of a 3D reconstruction is to create accurate 3D representation of an environment in a time-efficient manner. Traditional approaches often relied on first scanning the environment to gather the necessary images, and then passing the depth, color information for 3D reconstruction. In this method, the aerial scanning would be performed multiple times to gather sufficient amount of details, and the reconstruction would be done offline. This could become time-consuming, and the results may not always be accurate due to the textureless scenes or possible occlusions. In this paper, a novel online 3D modeling approach is proposed to solve these issues. The 3D model is incrementally reconstructed in real time to provide reconstruction quality feedback, and also based on this heuristic information, the drone will continually travel along the updated path to cover the low quality surfaces and to improve the stereo matching performance. Before discussing the details of the paper, let's cover some basics. First, multi-view stereo. So what is the multi-view stereo? Well, multi-view stereo is a basis of the 3D model construction. It is a general method that takes images of an object or a scene from multiple viewpoints, as you can see right here, to produce a 3D model of an object. The images from multiple views are needed for calculating the depth of an object. Also, the certain points on an object, let's say a point P in this image, may not be visible from a single viewpoint, which these unvisible viewpoints will include point view 1 and 2. And this would require images from different views to gather information about those points. So in this example, to get information about point P, you would have to observe it from viewpoints such as 4 or 5. It is noteworthy that most of the times the multi-view stereo is performed offline after the processed images have been acquired. So unlike the method proposed in this paper, finding an optimal view trajectory often requires more than a single exploration. A common approach to finding an optimal trajectory is known as explore, then exploit method. So let's find out why this method is named in such a fashion. So during the explore stage, a drone travels along a fixed trajectory to gather images of an environment. Let's say this is called the initial trajectory. Then this information is used to generate a coarse 3D model. And after the coarse 3D model has been generated, the information from this model is used to generate the optimal trajectory. So this is why it's called the exploit stage. So in the exploit stage, the information about the reconstruction quality based on the coarse 3D model is utilized to generate the optimal trajectory. So the drone travels along this new trajectory to gather the information needed to generate a higher quality 3D model. This process is effective in gathering the information for accurate 3D reconstruction. However, it can be inefficient as overlapping trajectories can be generated and requiring the drone to visit the same areas multiple times. As you can see right here, some of the sections will be visited multiple times. The overall system of the active 3D modeling framework can be divided into two main modules. First one is the online 3D modeling module, and secondly, the path planning module. These modules pass information to each other in an iterative fashion so that the view path can be continually updated to incrementally build an accurate 3D representation. The online multi-view stereo is performed through three main steps. First, the depth map of an image is obtained. By pixel-wise stereo matching in real time, the depth maps of this image are sequentially integrated using a Bayesian estimation approach to calculate the converged depth estimates. However, this estimation method have more unconverged pixels when compared to offline methods. So the authors of this paper deal with this problem by extracting piecewise planar areas and applying the weighted least squares filter to them. This approach allows for modeling of large-scale areas while dealing with noise and outliers in 3D data. Then, the circle mapping. The circles containing information about 3D position, normal, color, weight, and radius are used to construct a 3D surface model. In the final stage called the loop closing, the surface model and the volumetric map is deformed in accordance with the updated information about the environment. So similar to the multi-view stereo module, path planning can be categorized into three steps. First, the global path planning is the first step. So firstly, a global path is generated based on the based on the coverage computed from the volumetric map. The goal here is to maximize the coverage of the unexplored region. For each cluster of volume, representative points are selected, and the A-star planner is used to calculate the minimum Euclidean distances to formulate a global path. Then, target surface extraction would happen. The target surfaces are extracted to decide which areas need to be examined more. This is done by reconstructing a surface model and comparing it to the adjacent surface models to calculate a confidence value. The areas with low confidence values are then selected for further examination. Lastly, the local path planning happens. The local path planning is done in a similar fashion to the global path planning. The representative points are selected for the target surface clusters, and the local path is created to follow these points. I have kind of briefly gone over the basic steps which this system would operate. So for those who are interested, I have attached the pseudocode for the path planning method at the end of the presentation. Please refer to it for further details if you're interested. Here are the results from the simulation experiments. The 3D modeling of highly textured surfaces, which is the Catholic Church, and relatively less textured surfaces, known as the Colorado State Capitol, is performed. The proposed methods are compared with the next best view and submodular coverage method, which are both based on explore then exploit approach. So since these two methods are based on the explore then exploit approach, as you can see on the left, the circular trajectory would be the exploration part. And then after the first initial exploration has been done, these two approaches will then exploit the information from the 3D course model. So from this results, it can be noted that the proposed method only required a single exploration trial to generate the 3D model. So let's take a look at how this is done in real time. Sorry. So as you can see here, initially the proposed approach seems a little bit slower because it doesn't go through the circular trajectory, which is the explore stage in the explore then exploit method. But as time goes on, you can see that the proposed method performs much faster than the traditional methods. All right. The evaluation criteria are largely categorized into path efficiency and modeling quality. The path efficiency are based on the completion time and total path length. The modeling quality include accuracy and completeness, which are obtained by calculating the mean errors and the percentage of surface points that have distance errors smaller than the thresholds. The proposed method had the best performances in terms of path efficiency. As you can see, it took the smallest amount of time, or the shortest amount of time, to traverse along the optimal trajectory, which was also shorter than the trajectories that were proposed in the other methods. Also, as you can see, the proposed method achieved the best modeling quality in both the terms of accuracy and the completeness. So before wrapping up the presentation, let me quickly go over some of the strengths and weaknesses of the paper. So there are some obvious strengths in this paper, in this study. First one is that obviously it requires a single exploration trial, making it very much time efficient. And judging from the experimental results, despite going over the path only once, it can generate very accurate 3D models. And lastly, although the author wasn't 100% sure about this was the first study to implement online multi-view stereo system for modeling unknown structures. And just by reading through the paper, it wasn't clear to me what were the obvious weaknesses. So I had to think a little bit and take some guesses. So these are my personal opinions. So I think the first weakness of this paper is that this method is yet to be tested in a real world environment. The experiments were only done in a simulation. And to me, it seems kind of obvious that since all this process is done iteratively in a real-time fashion, this is going to take a lot more computational power compared to the traditional methods. So, all right. So thank you for listening to the presentation. And as I have mentioned before, I've attached the pseudocode for pathfinding algorithm at the back of the presentation. So please take a look if you're interested and make sure you do the quizzes. Thank you very much.